Every single day, chat applications process over 100 billion messages. To do this successfully, a system has to capture a text, route it across the world, and deliver it to a specific device in milliseconds, all while maintaining absolute privacy. We are going to map out the exact architecture that makes this possible, following the same engineering principles used by platforms like WhatsApp and Signal. To build this, you need a basic understanding of client-server communication and a blank canvas, either a digital diagramming tool or a piece of paper. By the end of this exercise, you will have constructed a working blueprint that successfully balances high-speed concurrency, persistent data storage, and military-grade encryption. Step 1 is establishing the transport layer. We need a way to keep a continuous pipeline open between millions of mobile phones and our backend servers, so messages arrive instantly. Older applications relied on HTTP long polling, where the client repeatedly asks the server if a new message has arrived. This approach forces repeated handshakes, flooding the network with overhead and quickly draining mobile batteries. To fix this, draw the first component of our architecture, a WebSocket gateway. This acts as our connection manager. Instead of repeatedly polling, the client establishes a single, persistent TCP connection with this gateway. When the backend receives a message, the gateway acts as a traffic controller, immediately routing that payload down the open pipe to the correct active user. If your goal is sub-200 millisecond message delivery, full duplex WebSocket connections are the mandatory standard. Step 2 is the data layer. A unified database will fail under this kind of load, because user profiles, chat metadata, and raw message logs all require entirely different processing speeds and access patterns. We solve this with a polyglot persistent strategy. Add a relational database, like Postgres, to your diagram. We use this specifically to store highly structured, frequently updated data, like user accounts and group memberships. For the messages themselves, we need a NoSQL database optimized for high-velocity writes, like Apache Cassandra. We partition this table by the chat ID and order it by the timestamp, ensuring fast sequential retrieval. Next, add an in-memory cache using Redis. This layer tracks active user sessions in real time and manages the pub-sub routing across our different servers. By splitting our storage based on the specific data type, the system scales horizontally. Your chat history loads smoothly, whether a conversation has 10 messages or 10,000. Step 3 is the security layer. Our servers must route billions of messages without ever being mathematically capable of reading the envelopes. To achieve this, we implement the Signal protocol. The process begins with a key agreement framework known as the X3DH handshake. This diagram maps the initial X3DH handshake, where Alice and Bob exchange public identity, signed, and ephemeral keys. This establishes a shared secret. The derivation equation shows the final secret key, SK, is derived strictly from these exchanges, which the server cannot compute. With the initial secret established, we apply the Double Ratchet algorithm. This derives a brand new, unique encryption key for every individual message sent back and forth. Because the key rotates forward with every message and cannot be calculated backward, we achieve forward secrecy. If an attacker somehow compromises a phone today, they cannot use that key to decrypt the conversations from yesterday. True end-to-end encryption strips the server of its decryption capabilities, turning it into a fast, blind router of ciphertexts. Step 4 is the state layer. We need to track the exact life cycle of a message, knowing precisely when it is sent, delivered, and read. Add 2 final components to the backend, a present service and a distributed message queue, such as Kafka, to handle users who are currently offline. We track receipts using an event-driven state machine. The server marks a message sent upon arrival. It transitions to delivered only when the recipient's WebSocket connection sends an acknowledgement. It transitions to read when the user actively interacts with the chat UI. If the recipient is completely offline, the system skips the direct WebSocket route. Instead, the message drops into the Kafka queue, which triggers a push notification through Apple or Google's external servers to wake up the user's phone. Meanwhile, the present service updates a user's last seen timestamp. It logs this by either tracking a continuous pinging heartbeat over the active WebSocket or by recording the exact time of their last action directly into the Redis cache. Managing state tracking asynchronously keeps the user interface perfectly synced with the backend databases, eliminating the need for the client to manually poll the server for updates. Your diagram should now resemble this, a fully integrated real-time chat architecture. We built a persistent transport layer to handle millions of connections, implemented a polyglot storage system to separate heavy writes from structural reads, locked it down with zero-knowledge encryption, and applied an event-driven state machine to track message delivery. To expand this system further, your next challenges would be adding a fan-out service to duplicate messages for group chats and attaching a content delivery network to handle large media files. You now hold a scalable, secure blueprint capable of supporting hundreds of millions of users without sacrificing speed or privacy.